Hi everyone, I'm KK and I work in NVIDIA. I'm very sorry for my voice, but sometimes it happens. In my talk entitled From Backpropagation to Enterprise Deep Learning, we will cover backpropagation up to enterprise deep learning. I see some of you are very surprised. You didn't expect that. But the journey from backpropagation to enterprise deep learning is like 5 years of academic knowledge and maybe another 5 years of professional experience. We have 38 minutes, so I need to be very fast. By the way, you must have heard that in NVIDIA we do a lot of deep learning because we can. Backpropagation is fundamental algorithm of every deep neural network, and backpropagation is like pregnancy. Only a mother understands pregnancy, and only a neural network can understand backpropagation. So we will start with an experiment where we will all experience backpropagation ourselves. You will be neurons, and I will fire some signals at you, and your job is to respond 1, then you raise your hand, or -1, and then you nod negatively. Let's practice. 1. Okay, -1. Perfect. And also, please prepare your wallets, because for each wrong answer, you need to pay 10 Polish zlotys. The organizers will collect. Okay? Ready? So I'm shooting my first sample at you. 1 or -1? Okay, I see some hands in the air. But unfortunately, this was -1, so the organizers, please collect 10 zlotys from losers. Another signal, 1 or -1? Okay. Unfortunately, this was -1 again. Another sample. 1 or -1? Oh yeah, come on. I see some hands, and it's very good because it's 1. And now I think you are tuned. Your neurons already understand a little bit, so it's time for a final test. 1 or -1? Yeah, more hands in the air. I like it very much. Ladies and gentlemen, girls and boys, you are officially trained and thoroughly tested reggae detector. Congratulations. A baby would need more training. For you, it was easy because in your brains, there is not much going on anymore. I mean, no offense. But now, we will write a neural network which, given a song, will itself guess its type of music, its gender. And we will write it from scratch. So if there is anyone here for whom AI is still magic, apologies, but the spell will be broken. If there are some marketing guys here maybe, or investors, coding session for you might be a bit painful sometimes, but I strongly believe it will not kill you. It will make you stronger. But first, a few words about music. Perception of sound takes place in the spectral domain. We don't hear samples, we hear frequencies. For example, this, it's A4, it's a sine wave with frequency 440 Hertz. This one, it's E2, 82 Hertz. Now let's record something. This is going to be note A. Okay, now record some melody. And a song in the rhythm of ska. There's hands in the air. Okay, the reggae detector is working. Okay, now we put our recordings into the project folder. We already have Marley, Vivaldi, and Metallica there. So we put our song. We have an empty main, as you can see, nothing is here, and some of my utils, like for showing pictures, etc., nothing fancy. Let's now create a Python file, we call it dataset, where we define the class to handle songs loaded from the path on the hard drive. We will use Libroza library to load these songs from the given path as wave samples recorded with a given frequency of sampling. N will be the number of samples, so the length of our wave. And let's create a plot method to draw such a song. Let's open a figure for 2 plots and first draw their wave in time. Time here is, of course, the index of samples. It's from 0 to n, spaced with the sampling frequency. Very simple. Let's display the figure, and we are done. And inside the main, we'll just create an object to load our first song from the path, which we just saved it, and we will draw it. So we are about to see a few seconds of our recording. The first one, note A, we will zoom in to 1 millisecond, and we'll see strongly distorted due to very poor laptop microphone, but it is a sine wave, okay? We can see about 4.5 periods here, which in this 1 millisecond window gives frequency exactly 440 Hertz. So note A. To see it even better, let's draw an artificial note A. So the note A 440 is, let's say, a tiny sine wave with a frequency of 414 time, but times 2 pi, because NumPy is in radians. We draw it, and let's run. Of course, we hard-coded 440 because we know I played note A, and that's why our sine wave correlates very beautifully here. If we wanted the computer to guess what note it was, we would have to generate a whole spectrum of these blue sinusoids and calculate which one correlates best with our orange signal, right? Such an operation is actually existing, and it is called FFT, Fast Fourier Transform. Have you heard about it, FFT? Yes, some people heard about it. A little digression for Polish audience, like FFT, almost everything in any field has 3-letter abbreviation, and I love them too, but please be aware, sometimes when you use abbreviations, you need to be very, very careful. Let's calculate such an FFT spectrum for our song, and let's draw it. FFT returns complex numbers, so we take absolute, we take FFT from NumPy library, we call it on our wave. Let's just normalize the values, and we will plot our spectrum and launch. And we'll see, hopefully, the maximum around 440 Hertz. Yes, you can see it. In other words, look at my laptop. She calculated itself that this was 440 Hertz. We didn't do it. We didn't tell her anything, but she already knows. Let's load the second recording. Do-do-dee-do-do-do-dee-do, right? And on the right, maybe I will show you. On the right, yeah, you can see the notes I played and their harmonics. And on the left, you can see that I was hitting the string 4 times per second, do-do-dee-do, right? And somewhere here in 1 Hertz, you can see that the whole thing has a visible periodicity of around 1 Hertz, like do-do-dee-do, right? This means that the computer already knows what rhythm we played and what notes. So let's simplify it even more. Let's partition our spectrum into 5 intervals in the human audible range from 0.1 to 10,000 Hertz. And let's calculate average in these intervals. And this trivial function of mine will return 5 ranges and 5 average values, so the embedding of our song. Now, instead of talking, let's just draw it for the third track, our umcia, 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 ska. You can see umcia, umcia here. It's about 2.5 hertz. That was the rhythm. You can see it very precisely. But more importantly, in orange, you can see whole spectrum average in 5 intervals. The slow, medium, and fast rhythm, and then amplitudes of low and high frequency notes. So instead of thousands of samples, we now have a 5-sample description, and let's hope this will be enough to find the differences between music genders. Here's how it looks like for our training songs. For each song, we have it reduced to 5 wide samples, okay? Okay, now a real neuron in our brain while listening to Bob Marley has some state bias, and it accumulates the weighted signals from synapses, and if the weights are trained properly, it activates accordingly. Our artificial neuron perceptron will do actually the same. We can also combine it into a multi-layer perceptron, MLP. And now we are about to load our songs and our embeddings with data loader, which we just created actually. And we will build a sequential model consisting of linear multiply-add layers that will multiply the inputs by weights and add them up, followed by a tanh activation layer, which will turn our result into a number in the range of -1, 1, so our response. A little digression again, tanh is a very old activation function. You might have heard about it. This is what it looks like. It does the job. Equation, not trivial, but very sexy. However, today the world is dominated by ReLU. This is what the function looks like. It's just y equals x, but always positive, nothing more, but the world has gone crazy. ReLU has penetrated into the world of pop culture and art. Okay, we covered loading the songs. Let's go back to our empty main. We will load songs compressed into 5 samples, and the output of the model will be just one number between -1 and 1. And the training data loader will create song objects for Marley, Metallica, and Vivaldi. But before we create and train the network, let's just show ourselves this data in the console, okay? So we will iterate over our 3 songs from the data set and show X, which is embedding of the song, and Y, which is reggae or not reggae, 1 or -1. Okay, we have it. You can see we have 3 results. First is for 5 numbers of reggae, and it's 1 because we know it's reggae. Then we have 5 for Metallica and 5 for Vivaldi, both of them -1 because they are not reggae. Okay, now we would like to write a model which will guess itself, this 1 and -1, getting only embedding of the song. We will show the result in a moment, but we need to create this model. And as we showed in the slide, our 1 neuron brain is a sequential connection of linear layer that receive 5 input samples and passes 1 result to the activation tanh layer. Let's add our definitions. Alt-enter, Alt-enter. Okay, linear layer will take n inputs and return n outputs, and these inputs will be multiplied by weights and added together. Very simple. And we have as much such multiply adders as we want, so I will write it down, but it depends how many outputs we need. Actually, in the beginning, we have only 1. Multiply adder is a piece of neuron that has bias and weights. We'll define them soon, but first let's define the call method. Calling such neuron should return its initial state, it is its bias, to which we add all inputs multiplied by weights. Very simple. So, to the initial state, we will add the weights, the weighted inputs from the synapses, and we return out. And now we return to the bias and to the weights. These should be just random numbers. In the beginning, your brain knows nothing, so it's initialized randomly. It should be float values. But right away, let's wrap them within some objects. Let's call such object value. And let's keep our original float in the data field. Actually, this doesn't help us anything at the moment. It complicates things, to be honest. And why? Because this is an object now. It doesn't know how to add, because it's not a built-in float anymore. And we really need to be able to add, to subtract. So we must define for our value add, multiply, negate, subtract, and square and tanh operations, because they will be useful to us. And now very trivial, we'll just adding two values returns a value whose value is the sum of input values and return result. Very trivial. For multiplication, it's the same, just multiplication. We'll define negation as multiplying by -1. Subtraction is the addition of the negated number, and square, which just returns value squared. And of course, tanh, which returns tanh. Okay? We will use tanh function from the math module for this. And we can call, now let's call a list of multiple values a tensor. User can initialize a tensor with a list of values, very simple. Tensor, just a list of values, nothing more. But I write it immediately as comprehension, because if they are values, let's take them as values. But if they are scalars, let's wrap them into values for the user. Okay, since we have our tensor, let's go back to multiply, add, and define bias as tensor of randomly initialized values, one number actually here, and weights, which we also draw randomly, but there are several of them depending on how big a neuron is. Now, calling linear layer will, of course, call all its neurons on the given input and return list of results for each neuron. And we have a tensor defined, so let's return a tensor out of this. tanh is a layer that will activate tanh all inputs and return result as a tensor. Again, trivial. Sequential layer, finally, is a concatenation of our layers, which will take each layer, call it, and pass the result to another layer, and so on, and finally return the result to the outside world. Okay, we can run the program, and for each song, we have Y predicted. So, ladies and gentlemen, we have created a program to predict music gender from a song. It's done. Are these results correct? Of course not. They are not correct. We have a baby who didn't yet learn anything. In this case, it answered, well, I guess it's reggae. I guess it's reggae for all of the songs to any music, but actually it's random. So let's define a constant seed for our random generator to be able to repetitively analyze our results. And let's calculate the loss. It is how much our baby owes us money for a mistake. Let's show it on a screen so that everybody can see it. This should motivate our baby to learn faster. And how we'll calculate this loss? For example, as a mean square error. So let's define this trivial class, which will take tensors A and B, one-dimensional tensors for a start, and we'll return their difference squared. And we run to see that for this example, for example, for reggae, you can see this baby owns us $3, more or less. That's what we expected. It's a very big loss. But now at least there's a pressure, okay? So we wrote the foundations of our network. Let's refactor it a little bit so it has some structure. Let's create a package as decent programmers would do. Let's call it framework because it's a catchy name and it fits here. I will create NN module like neural network and data module. And that's it. Value and tensor will move to the data module because these are data structures, value and tensor, Control X, Control V. And of course, layers and the loss will move to the NN module, Control X, Control V, and we have it easy peasy, lemon squeezy. We fix imports. And let's put import of our module and our tensor in the init of the package. And as my grandmother used to say, use it or lose it. Okay, now let's fix our layers which are no longer available locally because we need to get them from our NN module of our framework, which we just created. And let's run again. But we expect everything to work the same, yes? Because it's actually only a refactor. We run it and okay, we are so excited to have our network return something. That's clearly a first step. But as we already observed, the network is stupid. In order to make it learn anything, these random weights have to draw conclusions, be aware of mistakes, and know how to fix them. So let's make a first step in this direction. Let our value not be just a float, but let's make it aware of what operation it came from and what operands participated in that operation as its parents. So here, for example, the resultant out is a value which knows that it was created during addition, and it knows its mom and dad. Value created during multiplication now knows also who is it in the graph. The value knows this one that it was originated from squaring, and this one from know its roots, and so on. And what this gives us, attention, and catch your pens, please, because to my visualization we can add a model that is a graph. And since it is a graph, it can be shown. KK graph visualization, KK is me, that's why it is called this one. And now we are talking, because if somebody got lost, now they are found. So where we are, we uploaded the embeddings to the network. This network has some random weights W, the blue ones. The network multiplied everything, added together, and got some result, right? After activation, we have minus 0.8, which differs a lot from our desired one, as much as 1.8, which, when squared, gives us 3.2, quite a big loss. So the network is angry. No one wants to lose anything, yes? But here we are. This is what we have written so far. And what we need now, we need to give our network some tools to decrease its loss, knowing that it can only control the weights. It cannot change the input data. It cannot change the loss of mathematics. The weights are only parameters. But that said, you have to know that when Chuck Norris trains the network, the input data is actually adapting to the random initialization. We don't have Chuck. What we have is basic algebra. So let's try to figure it out very quickly. How to reduce the loss by, let's say, 0.2. Yeah? Our loss is the result of a square function, and 3.2 was created by squaring y 1.8 and minus 1.8, and here the slope of this function is very steep. The derivative is of x squared is 2x. So locally, for our minus 1.8, it's almost minus 4. So to reduce the loss by 0.02, you need to add here 4 times less to the input. It is more or less 0.05. How to increase this by 0.005? It was created as a result of subtraction, and derivative of the sum or difference is just 1. So to influence this result by 0.055, we have to add the same amount to one of the inputs. This value was created as a result of tan h function. Its input here was minus 112. So the derivative of tan h here is minus 1 tan h squared. So in this place, the slope is quite small. It's about 1/3. So to increase the result by desired 0.005, we must add 3 times more to the input. It is 0.015. Now this one was created by summing, and the derivative of summing is 1 again, so here no influence, it gets the same. And finally, 0.03 is the result of multiplying our weights by 0.3. And derivative of multiplication cx is c. So we need to add almost 3 times more to this input to get what we want. And this is more or less 0.05. So now the question is, let's check it. If we add 0.05, will the input be smaller by 0.02? I mean the loss. Let's check it. In our model, in the first layer, very quickly, we add to the multiply adder to the last weight, we add 0.05, and we run our predictions. Let's see the graph before and after, and we run everything. Before, our loss is 3.27, and after, 3.25, which is 0.02 less. Coincidence? I don't think so. Let's summarize. How changing any input influences its direct output? We estimate this as a local derivative, and we can directly calculate it everywhere. Indirectly, we can calculate such an impact with a simple chain rule. So how do I influence the loss? How do I influence the influence on the loss? How do I influence the influence on the influence on the loss? How do I influence the influence on the influence on the influence of the loss? And how do I influence the influence on the influence on the influence on the loss? Such estimation of the indirect influence of value to the loss is called gradient. And as you can see, it is calculated by backpropagating the gradient from the loss. So our value has now magnitude, but it also has a gradient and a backward function that will propagate this gradient backward to its parent. And as we just shown, it receives this function when defining the parent operation. If it was addition, the derivative of addition is 1, and the defined backward operation will be given to the out object created here when addition is called. And as we explained in a second, in the chain rule, backward will compute parent's gradient as local derivative of the operation multiplied by the gradient it will get from the child. Of course, sum has 2 parents, so the gradient will propagate in both directions. And let's paste this into every operation and just replace the derivatives. So we copy it and paste it to all of the operations and just replace the derivatives. So for example, here the derivative of x squared is 2x. The derivative of tan h is 1 minus tan h squared. And okay, we can call the backward on the loss now, and we'll look at KK visualizer. We run forward, backward, and in orange we can see gradient for each value. So we know how changing each of the value will affect the loss. So let's update the parameters. By parameter, I mean each weight and each bias of our model. It is the parameters that can actively change. So to reduce the loss, let us such parameter go down by the gradient by a little, okay, maybe 0.1, because it's non-linear function. And let's go forward, backward, update, update, and we have it. Loss 0.09, prediction 0.7, so almost 1. At the moment, our model has already tuned quite significantly into Bob Marley. Easy, man. We played Bob once, let's make it listen to Bob 4 times. I could listen to Bob Marley all the time. What is 4 times for the machine? 1, 2, 3, 4, and prediction. Okay, we have 0.9, which is almost 1. This neuron would kill itself for Bob Marley, and I respect that. If we train 1 neuron, let's finally train a bigger network. 1, 2, 3. We have 3 layers. In the first, 2 neurons. In the second, let's put 4. And only in the third, 1 single neuron for calculating the output. You don't know this, but at this moment, KK Visualizer in the background is submitting a ticket to IT to purchase bigger monitors. And I love watching how the network learns, like any parent. A large network is harder to learn, but will embrace much more information. So let's finally show it to other songs, not only Marley, so we'll not break after Marley. And let's disable KK Visualizer and just look at the console. But I'm telling you, this is going to be bad. In the last iteration on Marley, we have a mistake for $2.5 again. Let the model pay and let it listen more. 40 times. Let's do it 40 times. Imagine you play someone Marley and Metallica and Vivaldi, and after 40 times you ask, you got this? And they say, no, I don't get this. $2.2. My grandma would tell him, you should learn more, little boy, give him 100 times. And now it will be fine. I'm telling you, it will be very beautiful. But behind this happiness, there is a bit of embarrassment. After 100 times, when the music ripped off your brain, the guy suddenly like, yeah? Well, you can see we have 0.9 on Marley, minus 0.9, minus 0.9 on Hetfield and Vivaldi. The loss is less than a penny. Very cool. We are very happy. But why did it take so long? It's simple. Because mean square error loss is not suitable for classification. Much better, as you can see, is log loss. For example, here such a mistake by 10% is really irrelevant. Here, if someone admits he guesses almost 50-50, we will not cut his hand for that, right? I think it's a perfect example because when Marley fans get really engaged into their music and culture, actually Vivaldi and Marley start to seem almost the same. But now, if someone swears with his right hand that he's right while what he says is a sacrilege, they will pay with their right hand. So, should we code log loss now? Nah, it's boring and we've had enough. So attention, catch your pens again because I will delete our entire framework package. Gone, deleted. Red import, let's comment it. Red all around me, nothing works, panic, oh my God. But now look at that. In place of our framework, we will import PyTorch. And nothing screams, everything green. So does the almighty and mysterious PyTorch have identical interface? What just happened? We were writing our own network from scratch, like some students. Students, I respect you very much, learn a lot and come, I invite you to my network. And what we got identical results as PyTorch and identical interface. So actually, somehow, we wrote basic PyTorch from scratch. Conclusions? Frameworks are no magic, really. The cool thing is that in PyTorch, we have a lot of ready-made things, and you don't have to write them anymore. So I'm showing here a diff. So what we have written so far versus the version we would have in 5 minutes. The most important, of course, is changing loss to mean square, from mean square error to cross entropy. But if someone wants something more, control space, and there's a lot of other things. We made our network bigger. You can see we added more neurons. We changed the output size to 3 to distinguish all 3 music styles. And we throw out our SAT data loader and put a PyTorch data loader, which itself iterates through subfolders with waves. And you can see we will use Gdzan dataset with songs that I downloaded from the web. Small digression here again. I personally love very super intuitive names. Dataset with waves in separate directories per gender, I would probably call Gdzan. We run this. This time, we evaluate our model on every epoch with a collection of songs that the model has never seen. And after hundreds of epochs, you can see our model can correctly distinguish the gender 93% of the time, which is a pretty good result for the network written so quickly. Now, absolutely the most important thing at the end, .CUDA. One little word that you add to the model and to the data, and the whole thing suddenly moves into space, or to be precise, into NVIDIA GPU. Oh my God, it already finished, sorry. Buy GPUs, move your models to CUDA, train like pros. Otherwise, don't say, I haven't warned you. Okay, we simplified a lot, but if somebody would like to learn more, I recommend materials on the web, especially in NVIDIA Developer Program. What we did, we wrote MLP from scratch, but for a foretaste of real deep learning products, I invite you to NVIDIA Deep Learning repository, which I take care of. It's open source. Hit it, leave a star, fork, have fun. We have quite a lot of models there and also pre-trained models for NGC. Of course, perceptrons are just the beginning. Deep networks can be convolutional. So here, for example, in Black Mirror movie series, where a neurosurgical procedure was performed on this hero to segment his vision and remove people from what he sees. Very nice, promising technology. And anyone can do such segmentation themselves with Mascarcian network, fill the background with in-painting network, and apply some fancy blur at the end. And that's it. And here's the effect. Not neurosurgery, but augmented reality, but also not fiction, but actual scientific experiment. I call it ignore level master. Special architecture have been developed for graph analysis, for transformers, which dominated language modeling, as you know, probably from ChatGPT, reinforcement learning to train agents such as robots, self-driving cars, etc., and interdisciplinary models like NERV, which receive images as input, but process them into spatial relations and generate a 3D point cloud of amazing quality. Personally, I'm really excited about that because my colleagues from America did it, so you can touch me. Almost everywhere here, backpropagation was used, so everything you learned is exactly the same here. And now the biggest players in the industry need to make sure their deep learning solutions keep up with ever-growing technological advances and the demand of the consumers. So what does it mean? Models are trained in different frameworks using multiple libraries, all maintained by different teams at various cadences. Data sets are growing in size, variance. Companies constantly retrain their models and then provide inference services to a growing number of end users, which result in ever-growing demand for resources and means for the scalable implementation of AI solutions in various fields. Last but not least, hardware is designed and released to meet these dynamic demands, and we have a picture of an industrial-scale deep learning ecosystem which should be taken care of, and for which continuous integration, continuous delivery is a challenge on a completely different level than the one we get used to in our traditional IT world. We live in crazy times, you all know. I'm sure you have heard that many great people are signing petitions to stop working on deep learning models because they are not ready for them yet. Is there anything to be afraid of? Well, computers will not declare war on us. But let me show you what makes me feel anxious. We browse to NVIDIA Playground website, post a photo with your friends or family, and delete a few pixels here and there, and we watch how the machine would imagine that. Computers will train themselves on all the data available in the abyss of the internet. In this case, I have no idea what data this network was trained on, and what it knows about us, but it's a little worrying and embarrassing to me that my generated partner is always an Asian. 1, 2, 3. Thank you.